The update arrived quietly. No featured image. No highlighted alert. No language designed for the public. Just another routine entry added to the daily stream of observational data. And that is precisely why it mattered. Because buried inside that update was a signal that something still had not settled. Not visually, not dynamically, not internally. The parameters once again failed to converge. For most small bodies passing through the inner solar system, especially after perihelion, the pattern is predictable. Solar heating peaks, volatile loss accelerates, and then activity declines. Non-gravitational forces weaken. Residuals shrink. Orbit solutions stabilize. That is the normal arc. For 3I Atlas, that arc is still incomplete. When astronomers folded the latest astrometric measurements into the existing orbital model, using the same force terms, the same outgassing assumptions, the same rotational constraints, the solution did not improve, it degraded. Predicted positions no longer aligned cleanly with reality. The offsets were not dramatic, fractions of an arcsecond, small enough to be dismissed if they were random. They were not. The new data points leaned together, displaced consistently to one side of the predicted trajectory. Not scattered, not symmetric, coherent. That pattern immediately narrowed the explanation space. Random noise produces randomness. Instrument bias produces fixed offsets. But coherent residuals, repeating across independent observatories, indicate a physical influence that is real and incompletely modeled. Once again, the non-gravitational acceleration term had to be revised. In cometary dynamics, this term accounts for thrust generated by outgassing. As volatile material sublimates, gas escapes through vents and fractures, producing jets that act like weak but persistent engines. Near perihelion, these forces can measurably alter a trajectory. Afterward, they usually fade. This time, the adjustment was not simply a reduction in strength. The direction changed. The preferred acceleration vector rotated, implying that the dominant source of thrust was no longer aligned as it had been even days earlier. Either the most active vents had shifted, or the orientation of the nucleus itself had evolved. Possibly both. While the orbital team revisited the dynamics, the imaging data told the same story in a different language. Earlier stacked exposures showed an inner coma with a recognizable structure. A primary brightness axis extended outward from the nucleus, feeding a gently curved tail. Asymmetrical, but stable. In the most recent stacks, that coherence softened. The brightest region near the nucleus appeared rotated relative to earlier frames. One side of the inner coma thickened, becoming more diffuse. The opposite side thinned, breaking into a ragged gradient. Farther out, a subtle deviation emerged along the tail. Not a disruption, not a flare, a bend. Such features are not unheard of in active comets. But when they appear in close temporal alignment with renewed changes in non-gravitational acceleration, coincidence becomes unlikely. The geometry was changing because the forces were changing. Photometric analysis added a third, independent constraint. Rotation states are inferred by tracking periodic variations in brightness as a nucleus spins, exposing different surface areas to sunlight. A stable rotator produces a clean, repeating light curve. That is not what the latest data showed. When the new photometry was folded over the previously inferred rotation period, the alignment failed. Peaks arrived early, then late. Amplitudes varied from cycle to cycle. To recover a reasonable fit, analysts allowed the rotation period itself to drift and introduced small amplitude variations between successive rotations. The model improved. But the implication was clear. The object was not rotating in a steady state. It was wobbling. Such behavior can arise when asymmetric outgassing applies torque to an irregular body. Even weak jets, if persistently off-center, can alter spin states over time. In porous, low-strength nuclei, those torques may also redistribute internal stress. On their own, none of these observations would demand attention. Together, they converged on the same conclusion. The orbit was unsettled. The coma morphology was unsettled. The rotation state was unsettled. Not violently, not catastrophically, persistently. At that point, the central question shifted. Not what is changing, that was now clear, but why it continues to change. One interpretation fits the data without invoking anything unusual. After perihelion, surface volatiles are exhausted first. Heat absorbed during closest approach continues to diffuse inward long afterward. One interpretation fits the data without invoking anything unusual. After perihelion, surface volatiles are exhausted first. Heat absorbed during closest approach continues to diffuse inward long afterward. As deeper, more insulated reservoirs warm, activity can restart along fracture networks formed earlier in the encounter. Each newly activated pathway changes the balance of forces. Thrust shifts. Torque shifts. Illumination geometry shifts. The process is not smooth. It starts, pauses, resumes elsewhere. Temporary stabilization is followed by renewed adjustment. That framework explains why the system appears neither to be calming down nor spiraling out of control. It is still responding. Spectroscopic measurements offered tentative support. Compared to earlier observations, the ratio of gas emission to dust reflection near the nucleus shifted subtly. Certain species associated with deeper volatiles remained detectable, even as overall activity declined. That suggests new material is still being accessed, not merely recycled from the same exposed surface layers. Each release alters more than the coma. It alters the interior. Pressure pockets empty, voids form. Overlying material sags or fractures. If the structure were robust, these changes would damp out. The spin would stabilize. The jets would weaken. The orbit solution would converge. That has not happened yet, and that fact carries weight. Because in cometary evolution, the post-perihelion phase is often decisive. Some objects settle, quiet, and depart intact. Others do not. At this moment, 3I Atlas occupies neither outcome. It remains a single object, no confirmed fragments, no debris cloud. But the system has not found equilibrium, and that is why this latest update matters. Not because something dramatic occurred, but because, once again, the data refuse to say the process was over. When scientists describe a system as unsettled, they are not assigning intent. They are describing a refusal to settle into expectation. For 3I Atlas, that refusal has now persisted across every major observational channel. Orbital dynamics, photometry, imaging, spectroscopy. Each update was expected to reduce uncertainty. Instead, uncertainty has reorganized itself. That persistence is no longer incidental. It is the signal. Interstellar objects are rare by definition. Each one is a physical sample formed under conditions that cannot be recreated or directly observed. Different stellar radiation, different disk chemistry, different gravitational history. When such an object passes through the inner solar system, its response to sunlight becomes one of the few probes available into its interior. In that context, unpredictability is not a failure. It is data. A nucleus that continues to adjust after perihelion suggests internal complexity rather than exhaustion. It implies layered structure, uneven volatile reservoirs, and mechanical weakness sufficient for small forces to accumulate measurable effects. The continued drift in the inferred rotation period reinforces that picture. A body with uniform mass distribution tends toward rotational stability. An irregular one does not. It amplifies asymmetry. Likewise, the shifting orientation of active regions indicates that outgassing is not dominated by a single persistent vent. Instead, activity appears distributed across multiple zones that activate and fade on different timescales. This behavior contrasts sharply with many well-studied solar system comets. Those objects have endured repeated solar passages. Their most volatile components were lost long ago. Insulating crusts formed, activity damped, spin states stabilized. 3. I-Atlas has no such history here. It is encountering this radiation environment for the first time. Its materials were processed around a different star, under a different spectrum, likely within a different protoplanetary architecture. What remained preserved inside it is now responding to conditions it was never shaped to endure. That mismatch matters. Thermal energy absorbed near perihelion does not vanish when the object recedes. It continues to diffuse inward. Each internal layer responds on its own schedule. Each newly warmed pocket alters the balance of forces acting on the nucleus. From a modeling standpoint, this complicates prediction. From a scientific standpoint, it creates leverage. Every revision to the non-gravitational acceleration constrains where activity must be occurring. Every change in the light curve constrains shape and orientation. Every spectral shift constrains composition at depth. The fact that these constraints continue to evolve rather than converge implies that the interior itself is still reorganizing. The unresolved question is how that reorganization will end. One outcome is gradual damping. As deeper volatiles are depleted, activity weakens, torques diminish, rotation settles into a new equilibrium. The orbit solution converges. The object departs as an altered but intact remnant of another star system. This outcome is well represented among cometary precedents. Another outcome is progressive destabilization. Each new vent redistributes stress in a way that promotes further fracture. Spin changes amplify internal strain instead of reducing it. Structural integrity declines until the nucleus begins to shed material or fragment, not explosively, incrementally. Such outcomes have also been observed. At present, the data do not decisively favor either path. What they do indicate is that the system remains in transition, and transitions are where physical systems reveal the most. A quiet object tells us little beyond bulk properties. A fully disintegrated one reduces interpretation to debris dynamics. 3. Atlas occupies neither state. It is stressed, responsive, and still coherent. That intermediate regime is rare. It allows cause and effect to be observed directly. Small changes in solar illumination lead to measurable changes in outgassing. Outgassing alters rotation. Rotation changes illumination geometry. Illumination geometry feeds back into activity. The loop closes, then shifts, then repeats. This feedback cycle is seldom observable with such clarity. The interstellar origin adds further weight. The materials now escaping were not processed here. Their molecular abundances, isotopic ratios, and dust properties encode conditions from another planetary system. Each molecule released represents chemistry that survived ejection, interstellar travel, and solar encounter. The unsettled behavior suggests that this chemistry is being released in stages, not uniformly. Different internal regions are responding at different times. That staggered release offers insight into internal architecture, how the object was assembled, how it was altered, and how it has endured. Importantly, none of this requires invoking unusual mechanisms: thermal lag, porosity, asymmetric activity, rotational torque. These processes are sufficient to explain the observations so far. What remains uncertain is not how the changes occur, it is where they lead. Daily monitoring continues. Each update tightens constraints but stops short of resolution. The case remains open not because the data are poor, but because the system itself has not finished responding. From a scientific perspective, that is precisely the point. We are not observing a static object. We are watching a process unfold. And processes, unlike outcomes, can teach. For now, 3I Atlas remains unsettled. not as a dramatic label, but as a measured description of a body still adjusting to forces it has never encountered before. Whether those adjustments will damp out, cascade, or resolve in subtler ways remains unanswered. The data have not decided yet, and until they do, the most important question remains open. What does equilibrium look like for an object that formed somewhere else entirely?